So let's do a couple of examples here with the mean value theorem. Again, we're going to see if it can be applied. And if it can, then we're going to find the values where we have this guaranteed value of the derivative. In fact, we'll find the guaranteed value of the derivative and then find where it occurs. Okay, so let's take a look here. We have to make sure of our two conditions. That's the first thing we must do. All right, so is f continuous on the closed -2, 1? Well, again, we're looking at x squared here, a nice polynomial, so it has to be. Is f differentiable on open -2, 1? Polynomial, differentiable everywhere, it's good. Okay, this tells me MVT applies. Okay, so I know I can apply the theorem. So now there's two questions that I really want to think about. What is this guaranteed f prime of c? What is the guaranteed value of the derivative? Well, I would need to calculate what it's telling me is f prime of c is f of b minus f of a over b minus a. Okay, f of b, so then we're talking about f of 1 minus f of -2 over 1 minus -2. All right, our function is x squared, so f of 1 is 1 minus f of -2, our function is x squared, so we get 4 over 1 plus 2, which is 3. So we get -3 over 3, so we get -1. All right, so what have we actually found? We found f prime of c is -1. That's our guaranteed value of the derivative. Okay, so somewhere the derivative must take the value -1 on that interval. Okay, so then the next question, which again is not always going to be possible to actually do, but we're going to ask, what is c? Or really, what are the values of c if there's more than one? So now, because this is a simple enough function, we can actually figure out what the derivative is. Well, the function is x squared, so the derivative is 2x, no problem. Okay. And so all I'd be saying now is that I want to take this 2x and I want to set it equal to the guaranteed value of the derivative. So I'm just going to say 2x equals -1. All right, the derivative equals the guaranteed value of the derivative. And by simple calculation here, we can see x is -1/2. And then let's go back, take a look. The interval is -2, 1. That does occur on the interval, so our c is -1/2. Okay. We found that there is just one place, but one place was guaranteed, and indeed it was even on the interval as guaranteed by the theorem. Let's do another one. All right, f of x is square root of 2 minus x on -7, 2. All right. Is f continuous on -7, 2 closed interval? Okay, well, it's a square root function, and that's going to be continuous wherever it's defined. And in fact, it is defined all along here. So yes. Is f differentiable on open -7, 2? All right, this is not as obvious a question. So one thing we can do is we can take a look at the derivative and see if there's any issues with it. All right, so let's, oops, sorry. Let's take a look here. Let's calculate the derivative. So the function is 2 minus x to the 1/2, so 1/2 2 minus x to the negative 1/2 times, go inside and take the derivative of the 2 minus x, and you get a minus 1. All right, so we get minus 1/2 2 minus x to the minus 1/2, or another way we might see that is minus 1 over 2 square root 2 minus x. All right, so there's our derivative. So take a look at the derivative. What would it mean for f to be differentiable on this interval? It would mean that the derivative doesn't have any problems at any point in this interval. Okay, so at first you might say, oh, there's a problem. At 2, it's not differentiable. And you're right, it isn't. But 2 is not in open -7, 2. Right? So we're okay for the open interval -7 to 2. So in fact, we're good. And in fact, MVT applies. Okay? So even though we had a place where it wasn't differentiable, that wasn't in the open interval, and that's why it's important to look at the open interval for differentiability. Okay, so now that we have that, we know MVT applies, and so I'm going to ask, what is this guaranteed value of the derivative? Well, it's just f of b minus f of a over b minus a. So f of 2 minus f of -7 over 2 minus -7. So we get f of 2. Now remember, f of x is the square root of 2 minus x. So f of 2 would be 0 minus f of -7, 2 plus 7 squared root of 9, that's 3. Over 9, so we get -1/3. All right, so there is our guaranteed value of the derivative. All right, not our answer yet, but that's the guaranteed value of f prime. Okay, so we got to go a little further now. What is C? Well, we already calculated the derivative up above. We have that f prime of x is -1 over 2 times the square root of 2 minus x. And we're going to set that equal to this -1/3. Okay. Well, obviously, if you have -1 over the thing on the left and -1 over, so that means the two denominators have to be the same. So 2 times the square root of 2 minus x would have to be 3. All right, that means the square root of 2 minus x would have to be 3 over 2. Then I'll square both sides. 2 minus x equals 9 over 4. That would mean that x is, think about moving x to the right and then the 9/4 to the left. You would get 2 minus 9/4. So you would get x is, that's 8/4 minus 9/4, that's -1/4. And notice that that -1/4 does fall within our -7 to 2. So in fact, that's the value we were looking for. There is our C value. All right, another one here. Okay, so let's check this one here. We want to know, is f continuous on close to 6? All right, that's our first check. Obviously, this rational function here has an issue at 4. F is discontinuous at x equals 4, so no, this doesn't work. Since it's not continuous on the closed interval, we're done. MVT does not apply. I can't move forward in using MVT to make any guarantees here. That's it. So those are some examples of how we can use MVT by checking to see if we can use it, and then if we can, using it to find the information about the derivative.